pulls out the really important stuff, and basically gives you the shortcut to being genuinely clued in.
Yep, cutting through the noise.
Exactly. And today, we're tackling a big one. An icon you see absolutely everywhere, E pi c pure.
Oh, yeah. T-shirts, posters. It's probably the most famous equation ever.
It really is.
Yeah.
But the question is, do you really know what it means?
Yeah.
Like, beyond just recognizing the letters.
Because it's so much more than just a neat formula, isn't it? It was genuinely revolutionary. Changed how we saw the universe, linking things like mass and energy.
Things people thought were totally separate before.
Completely separate.
And that's what we want to unravel today. Our mission, if you will, is to get a real handle on these deep links between mass, energy, light, momentum, all of it.
And we've got some pretty surprising facts lined up, because impioca, it turns out, is really just the starting point.
Right. It's like the opening act for this much bigger, more elegant picture that explains, well, everything from how this sun burns to why, incredibly, a spinning baseball is technically heavier than one just sitting there.
Which is wild when you think about it. So we'll be digging into questions like, how much light is actually locked up inside mass?
Yeah, and can light itself have mass? That sounds weird.
It does, yeah. And what does a photon's momentum tell us about what it fundamentally is?
Okay, let's do it. Let's try and unpack some of this mind-bending physics, hopefully with, clarity, maybe a little bit of wit along the way.
Sounds good.
The foundation of equivalence beyond Eve C. Hoyt.
Right, let's start with the icon itself then. EFC4, for, decades now. It's been shorthand for, immense power, some kind of deep truth about the universe.
It really has. And fundamentally, it's saying mass and energy aren't just, connected. They're basically two forms of the same thing, interchangeable.
Like Einstein's phrase, mass is just congealed energy.
Yeah.
I like that.
It's a great way to put it, yeah. And to be super precise, the version people often mean is EM-C-J-C. Where EA is the rest energy.
Rest energy, okay.
Yeah, and EH is the rest mass. It's the energy something has just by existing, even if it's perfectly still. Think of it like this huge hidden reservoir of energy inside all matter.
And the huge part, that comes from the c, right, speed of light squared.
Right.
Which is just a ridiculously big number.
Oh, it's colossal. About 9 times 10 to the 16th in the right units.
Okay.
And that huge multiplier is the key. It means even a tiny, tiny amount of mass is equivalent to a stupendous amount of energy.
That's the core idea, isn't it?
It really is. And I mean, think about converting just 1 gram like a paperclip completely into energy.
Okay.
The energy released would be comparable to the Hiroshima bomb from 1 gram.
Wow. That really drives it home.
It makes it tangible, doesn't it? And this isn't just some abstract idea. It's literally what powers nuclear reactors, nuclear weapons too, unfortunately.
From the sun, right. That's the big one.
Absolutely. On a cosmic scale, that's how our sun shines. It converts something like 4 million tons of its mass into energy every single second.
4 million tons a second.
Every second. That's the energy pouring out that ultimately supports all life here on Earth.
The scale is just... yeah, mind-boggling. Okay, so let's talk about the M in the equation. You mentioned rest mass, M, but historically there was this other idea, relativistic mass. Caused a bit of confusion, I think.
It did, yeah. It's mostly fallen out of favor now, thankfully. Modern physics almost always talks about invariant mass, or rest mass, M.
Invariant mass.
And that's the fundamental inherent mass of a particle or a system. It's the same for everyone, no matter how fast you're moving relative to it. Like, every single electron has the exact same invariant mass, always.
So it's like its true identity.
Pretty much. The old relativistic mass idea suggested mass increases with speed, but that's, it's confusing. It's really just another way of talking about the object's total energy. The particle doesn't actually get heavier in its own frame.
Ah, okay. So the object's invariant mass, its inner stays the same, but as it speeds up, its total energy and momentum increase.
Exactly. And that's why it gets harder and harder to accelerate it as it gets closer to the speed of light. Not because its intrinsic mass changes.
Got it. That's a really important distinction. And what blows my mind is that this mass energy thing isn't just for, nuclear bombs or stars. It means any energy change in a system changes its mass. Like if I just squeeze a spring.
Yep. Infinitesimally, but yes.
Oh.
A compressed spring or a stretched one has slightly more mass because of the potential energy stored in it.
No way.
Seriously.
Yeah.
Same if you heat something up. You add kinetic energy to the molecules, right?
Yeah.
That energy adds to the total mass. Even the standard 1 kilogram weight in Paris.
Yeah.
Heat it by 1 degree Celsius, and it gains about 1.5 picograms. Tiny, but real.
So my hot coffee this morning was technically heavier than when it cooled down?
Technically, yes. And you mentioned a spinning ball earlier.
Yeah, is that true? Is the Earth heavier because it's spinning?
It is. The kinetic energy of rotation adds mass. For the Earth, it's something like over 10 million kilograms added just from its spin.
That's amazing.
But maybe the most profound example is inside the atom, something called mass defect and binding energy.
Okay, mass defect.
Right. When protons and neutrons bind together to form a nucleus, they actually release energy. It takes energy to pull them apart, so energy must be released when they come together.
Like becoming more stable.
Exactly.
Yeah.
And because energy has left the system, the final nucleus weighs less than the sum of the individual protons and neutrons you started with.
So the missing mass, that is the energy that was released. Like they're literally the same thing.
Precisely. That difference in mass, the mass defect, is the binding energy, just expressed in mass units using E means CS sorts. And that's the energy source for all nuclear power. Fusion in the sun, fission in reactors, it all comes down to converting a tiny bit of that binding energy mass difference.
So the sun converting hydrogen to helium, that 0.7% mass difference we talked about.
That's it. That tiny fraction becomes the sun's immense energy output. It really shows that a system's mass isn't just adding up the parts. It's the parts plus the mass equivalent of all the energy holding it together or moving inside it.
The universal framework, the energy-momentum relation.
Okay, that really does change how you think about what mass is. But hang on. We started with EMCO. EMCO, being for things at rest. Zero momentum.
Right. That was the limitation.
So what about moving objects? Or, even weirder, what about things like light, photons that have no rest mass? We need something bigger, right?
You absolutely do. EMCH is just one piece of the puzzle. And that brings us to what I think is really the master equation of special relativity, the energy-momentum relation.
The master equation.
Yeah.
Okay, I'm ready. What is it?
It looks like this. EMCT plus E squared equals PC squared plus M0 K squared squared.
Yeah.
Okay, a bit more going on there. A bit more, yeah. But this one equation connects everything. The total energy, E, the momentum P, and that fundamental invariant mass, M0. And it works for everything, particles, systems, massive, massless, and crucially, it's true for all observers in uniform motion.
So different observers might disagree on the energy E or the momentum P they measure.
They will, yeah, depending on their relative speed.
But they will always agree on the value of M0, the invariant mass.
Always. That's why it's invariant. It's the bedrock.
Now, I've heard people describe this equation using, like, a geometry analogy, something about Pythagoras' theorem in spacetime. Can you unpack that a bit?
Yeah, it's a really neat way to think about it. You know Pythagoras? A plus B plus B plus C SU for a right triangle?
Sure.
Well, you can think of the total energy E as the hypotenuse of a sort of abstract triangle in spacetime. The two legs are the energy related to momentum, PC, and the rest energy, M plus.
Ah, okay. So EPC plus M0 is like CM plus ME.
Exactly. And just like the lengths of the sides determine the hypotenuse, the momentum energy and the rest energy determine the total energy, and the invariant mass hero, it's like the length of one fundamental side of that triangle, constant, regardless of how the other parts change due to motion. It gives a deeper geometric reason why M0 is fundamental.
That's actually really helpful.
Yeah.
Visualizing it like that. And you said this one equation covers both massive and massless particles.
Beautifully. Let's take massive particles first things with M0 greater than 0, like electrons, protons, you, me.
Right.
If the particle is at rest, its momentum P is 0, right?
Okay.
So plug P is 0 into the master equation. E arrow plus M euro plus M euro so. That just becomes E arrow so.
It just pops right back out.
It falls right out. The famous equation is just the zero momentum special case of the bigger relationship.
That's so elegant. And this also shows how Einstein's physics sort of includes Newton's, doesn't it? It doesn't just throw it away.
Precisely. If you take the full equation for a massive particle moving slowly, much, much slower than light, and you do a bit of mathematical approximation.
Okay, I'll take your word for it.
Yeah. It simplifies to show that the total energy is approximately the rest energy, plus the familiar Newtonian kinetic energy.
Ah, so classical kinetic energy is just hiding in there as part of the total relativistic energy.
Exactly. Newton's physics works perfectly well as an approximation at low speeds, but Einstein's theory provides the full, more accurate picture that also works at high speeds. It subsumes Newton.
Didn't replace, just expanded. Okay, now for the really weird ones. Massless particles. Dot M euro equals 0, like photons. What happens then?
This is where it gets really interesting. Put m0 into the master equation, E EPC plus 0 late.
So that just means E equals BC. Energy equals momentum times the speed of light.
That's it.
That's it. That equation, EPC, defines a massless particle. Its energy comes entirely from its momentum. It has no rest energy because it has no rest mass.
And that means it can't ever be at rest, can it? Never. If a photon stopped, P0, then its energy, EPC, would also be 0. It would cease to exist. Its very existence is tied to moving at speed c, carrying momentum and energy.
The enigma of light, the photon.
Okay, that leads us perfectly into talking about light itself, the photon, which for centuries caused huge debates. Is it a wave? Is it a particle?
And the answer, wonderfully confusingly, is yes.
Yeah.
It's both. Wave-particle duality.
Right. We see wave behavior in things like,
Diffraction interference.
Mhm.
The classic double-slit experiment where light seems to bend around corners and interfere with itself, making patterns, pure wave stuff.
But then you have things that scream particle, like the photoelectric effect. I remember that one. Light hitting metal knocks electrons out.
Right, but crucially, whether electrons get knocked out depends on the light's frequency, its color, not just how bright it is.
Which is weird if it's just a wave spreading energy out.
Totally weird. And that's what Einstein explained in 1905, proposing these discrete packets, these photons. He said an electron only gets ejected if one single photon hits it with enough energy, and that photon's energy depends on frequency.
One packet of energy does the job, or nothing happens.
Exactly. And then there's the Compton effect. Arthur Compton firing X-rays at electrons.
And they scattered like billiard balls, right?
Precisely. The X-ray photons lost energy and changed direction, and the electrons recoiled, conserving energy and momentum in the collision, just like tiny particles bouncing off each other. That was killer evidence that photons carry momentum.
So yeah, wave sometimes, particle other times. It propagates like a wave, but when it hits something, it interacts like a particle.
That's the gist of it. It's one of the core mysteries and beauties of quantum mechanics.
So what are the key properties of this photon particle then?
Well, its energy, as Einstein showed, is tied to its frequency, f, or wavelength, EHF, or E Saishika, where h is Planck's constant.
So high-frequency light, like blue or ultraviolet, those are higher energy photons.
Correct. And its momentum, which Compton showed it has, is directly related to its energy, P equals EC, or, using the energy formula, P equals key.
Okay, P equals he. Momentum is Planck's constant divided by wavelength, so a massless particle carries momentum.
Wow. And it's inversely related to wavelength.
Yes. Shorter wavelength means higher frequency, higher energy, and higher momentum for the photon.
And this isn't just theory, right? This momentum is real. It's how solar sails work.
Exactly. Sunlight, trillions upon trillions of photons, hitting a large lightweight sail exerts a tiny but continuous pressure, pushing the spacecraft. It's radiation pressure, the momentum transfer from photons.
And laser cooling, too. That sounds bizarre, using light to cool things down.
It does, but it works. By carefully tuning laser frequencies, scientists can make photons selectively hit atoms moving towards the laser. Each photon absorption gives the atom a tiny momentum kick opposite its direction of motion.
So it slows the atom down, like a brake made of light. Essentially, yeah.
Yeah.
Repeated kicks slow the atoms dramatically, reducing their kinetic energy, which is temperature. You can cool atoms to near absolute zero this way. It's amazing.
It really is. So just to hammer it home, the photon is massless, meaning zero invariant mass, m0.
Correct. Zero rest mass.
Which is why it has to travel at c. If it could start, EPC means P0, E0. Poof, it vanishes.
It would cease to exist. Its nature is motion at light speed.
Okay, let's make this concrete. Compare a photon to, say, an electron, a familiar particle with mass. How do they stack up side by side?
Good comparison.
Yeah.
It really highlights the role of mass. So rest mass, electron, non-zero, about 9.11 by 10 aero kilojoule. Photon, 0. Big difference, number 1.
Okay.
Electric charge. Electron, negative 1 elementary charge. Photon, 0 charge.
Right.
Speed in vacuum. Electron, always less than c. Photon, always exactly c.
Dictated by that mass difference.
Absolutely. Energy momentum. Electron follows the full EPC plus, m0 plus EPC plus up. Photon follows the simplified EPC.
Got it.
Existence. Electrons are stable particles. Their number is generally conserved. Lepton number conservation. Photons. Well, they can be created and destroyed all the time. Think of turning a light bulb on or off.
They pop into and out of existence easily.
Pretty much. But both, interestingly, exhibit wave-particle duality. Electrons can act like waves, too.
Ah, true. De Broglie wavelength.
Right. But the core difference, the thing that dictates most of their behavior, really boils down to that first point. Does it have invariant mass or not?
Quantifying the connections, answering the big questions.
Okay, let's circle back to those big questions we started with now that we have this framework. First one, how much light is in mass? What's the quantitative answer there?
The most direct way to interpret that is, if you could convert mass entirely into light energy photons, what would you get? And the only way we know to do that 100% is particle-antiparticle annihilation.
Matter meets antimatter.
Exactly. Let's take a rather extreme example. Imagine you have 1 kilogram of matter and you annihilate it with 1 kilogram of antimatter. So 2 kilograms of mass in total.
Okay, 2 kilograms. Gone. What happens?
The energy released, you use E mc4 with M will take 2 kilograms. It comes out to about 1.8 times 10 e-joules.
Which is how much in real terms?
It's equivalent to almost 3,000 Hiroshima bombs from just 2 kilograms of mass converting entirely to energy.
That's almost inconceivable. And what form does that energy take? You said light.
Primarily, yes. In the simplest case, like electron-positron annihilation, you get 2 gamma-ray photons flying off in opposite directions to conserve momentum. For 2 kilograms annihilation, these photons would have unimaginably high energy and frequency and incredibly short wavelengths. So the answer is mass contains the potential for immense amounts of very high energy light.
Wow. Okay. Now the flip side, how much mass is in light? Which you said feels tricky because photons have me a row.
Right. It's subtle. A single photon traveling alone has 0 rest mass. But light carries energy. And energy, according to general relativity, curves space-time. It causes gravity.
So light creates gravity.
It acts as a source of gravity, yes. That's why starlight bends when it passes near the massive sun. The sun's gravity warps space-time. But the light's own energy contributes infinitesimally to that warping too. In this sense, light has a sort of gravitational mass equivalent to its energy divided by city supply. M equals E sub LO.
Okay, that's one angle. But you mentioned a thought experiment. The mass of a box of light.
Ah, yes, the box of light. It's a classic for understanding this. Imagine a box with perfectly reflective inner walls. Empty, it has some mass, M.
Okay.
Now you fill it with photons, light bouncing around inside. Each photon individually is massless, and let's say the light is bouncing in all directions, so the total momentum of all the photons inside adds up to 0. The box isn't moving.
Right. Light is trapped, but the box stays put.
Okay. Now, what's the mass of the system? The box plus the trapped light. We use the master equation again. E=PC plus M plus MO equal. Here, E is the total energy inside. The box's rest energy plus all the photon energy, E photons. And P is the total momentum, which is 0.
So E equals 0 vector plus M system C vector. The total invariant mass of the system times C squared, all squared.
Exactly. So E total air system C a vector. Or, rearranging the total mass of the system, E system, is the total energy inside divided by COSR.
Which is the mass of the box plus E photon COSR.
Precisely. The system as a whole has gained invariant mass equal to the energy of the trapped light divided by COSR.
So the box of light is heavier, even though the photons themselves are massless.
Isn't that something? It shows that the invariant mass of a system isn't just the sum of the rest masses of its parts. It includes the mass equivalent of any energy contained within the system: kinetic energy, potential energy, or in this case, the energy of trapped massless photons. It's like the mass defect idea, but in reverse. Contained energy adds to the system's invariant mass.
That really ties it all together. Okay, final question in this set. How much light is in momentum?
This one's actually the most direct for a photon, because for a photon, EPC, energy and momentum aren't independent properties. They are locked together by the constant C.
If you know one, you know the other.
Instantly. You can't change a photon's energy without changing its momentum in exact proportion, and vice versa. And remember, we also linked momentum to wavelength. P equals hit.
Right.
So specifying a photon's momentum immediately tells you its energy, its frequency, and its wavelength. A high momentum photon is a high energy, high frequency, short wavelength photon.
So for a photon, momentum isn't just a property, it's almost everything. It defines its energy and its wave characteristics completely.
In a very real sense, yes. For a massless particle defined by EPC, momentum captures its entire dynamic and wave nature.
Equivalence in action, real-world manifestations.
This is great. We've built up this theoretical picture, but you've been hinting all along. This isn't just theory. We actually see this stuff, this mass energy equivalence happening.
Oh, absolutely.
Yep.
It's fundamental to how the universe works, from the incredibly small to the incredibly large, and even in our technology.
So let's start with that 100% conversion idea again, annihilation. We talked about the extreme 1 kilogram example, but are there more common ones?
The most common, and one we use technologically, is electron-positron annihilation. When an electron meets its antiparticle, a positron.
Which is like an electron but with positive charge.
Exactly. They annihilate each other completely. Their entire combined rest mass vanishes and typically turns into two gamma-ray photons, each with an energy of 511 kilo-electron volts, totaling the 1.022 MeV equivalent of their combined mass, flying off back to back.
A perfect E-Memsi-Hawken conversion.
Textbook example. Proton-antiproton annihilation is more complex, produces a shower of other particles, but the principle holds total output energy matches total initial rest mass energy.
Okay, so that's total conversion. Then there are the partial conversions, like in nuclear reaction.
Right, these aren't annihilations, they're rearrangements. Only a tiny fraction of the total mass involved gets converted.
Like fusion in the sun. We keep coming back to that.
Because it's such a perfect example. 4 hydrogen nuclei, protons, eventually fuse into one helium nucleus. The helium nucleus is about 0.7% less massive than the 4 hydrogens you started with.
Only 0.7%, but on the scale of the sun.
It's colossal. That tiny mass difference becomes energy via equalated here. That energy is the light, heat, and neutrinos pouring out of the sun. That 4 million tons per second conversion is the 0.7% mass defect happening on a stellar scale.
And then the other side is fission, right? Splitting heavy atoms.
Yes, used in nuclear power plants and the first atomic bombs. A heavier nucleus, like uranium-235, gets hit by a neutron, becomes unstable, and splits into smaller nuclei plus more neutrons.
And the piece is way less than the original atom.
Again, yes. The total mass of the fission products is slightly less than the mass of the original uranium atom plus the neutron. That mass difference is released as energy, mostly kinetic energy of the fragments flying apart, and also gamma rays. It's still ECO, just a different way of achieving that bind.
So whether you're fusing light atoms or splitting heavy ones, you're tapping into that binding energy, converting a fraction of mass.
Precisely. You're rearranging nucleons into a state where the total system mass is slightly lower, and the difference comes out as energy.
And we actually use these principles in everyday tech. Like I know you mentioned BT scans.
Yes, positron emission tomography, a fantastic medical application that directly uses electron-positron annihilation.
How does that work?
Okay, so a patient is given a special tracer molecule tagged with a radioactive isotope that emits positrons, the antimatter electrons.
Right.
This tracer accumulates in certain areas, like metabolically active tissues, tumors, for instance. When the isotope emits a positron, it travels maybe a millimeter.
And then finds an electron.
And boom, annihilation, producing those two 511 keV gamma rays flying off in opposite directions. Detectors around the patient register these pairs of photons arriving at the same time.
Ah, and by tracking where those pairs came from.
A computer can reconstruct a 3D map showing where the tracer concentrated, revealing metabolic hotspots. It's literally imaging the body using antimatter annihilation based on EMC-AWA.
That's incredible. Direct EMC-AWA at work in hospitals. And what about the photon momentum stuff? Solar sails.
Yeah, solar sails are a real propulsion concept. Huge, thin sails designed to catch sunlight. The momentum transfer from countless photons reflecting off the sail provides a small but continuous thrust. No fuel needed, just sunlight. We've flown experimental missions already.
Free propulsion, basically.
Slow, but potentially very effective for long interstellar journeys. And then there's laser cooling, which we touched on.
Using photon momentum to slow atoms down to near absolute zero.
It's a cornerstone of modern atomic physics. By hitting atoms with laser photons tuned just right, you can remove almost all their kinetic energy, cooling them to microkelvin or even nanokelvin temperatures. This lets scientists study quantum phenomena in incredible detail. It's precision control of matter using light's momentum. Outro.
Wow, okay, so we've gone from just seeing EMCMEO on a t-shirt to, well, seeing how it connects to the energy-momentum relation, E is PC plus MUS, MUUG, which governs everything.
It really ties it all together, doesn't it? And the big takeaway for me is always that invariant mass, that's the fundamental property that stays constant for a particle. What changes with motion is the total energy and momentum.
And that old idea of mass conservation, it's really just an approximation that works well when energies are low, right?
Exactly. In the everyday world, mass seems conserved because the energy changes are tiny, so the mass changes are minuscule. But in nuclear physics, in particle physics, you clearly see mass converting to energy and vice versa. The real conserved quantity, the ultimate currency of the universe, is energy.
Energy is king.
Energy is king. Mass is just one form it can take.
And it's amazing how interconnected it all is. These aren't just separate equations for different situations. It's one coherent picture, the energy inside a tiny particle that connects to how galaxies are structured. The way a photon behaves tells us about space-time itself.
It's a beautiful tapestry. Relativity, quantum mechanics, they're not separate subjects, really. They weave together to describe reality, from the subatomic level right up to the cosmos.
So here's a final thought for you listening. Think about just heating your coffee, like we said, or even just the earth spinning beneath your feet. Those simple everyday things involve tiny, tiny shifts in mass because energy is involved.
It connects the mundane to the cosmic.
Exactly. That act of heating water, or the Earth's rotation, is fundamentally tied to the same physics that powers stars and bends light across the universe. So maybe ask yourself, what other hidden energies, kinetic or potential, might be subtly changing the mass of the world around you in ways we don't normally even think about?
It's a fascinating rabbit hole to go down. Hopefully, this deep dive has given you some tools to appreciate that deep, elegant unity in the physical world.
Yeah, keep asking those big questions. Keep digging deeper.